Preamble. First of all, thank you very much to the organizers for inviting me to give this talk about the energetic universe. I'll be focusing on the slow transients, so synchrotron transients. Sarah Burksblore will focus on faster transients for those of you who like pulsars and FRBs and so on, and she'll be talking on Friday. Just before we get started, I'd like to pay my respects to the traditional custodians of the land that we're meeting on, and it's great to be here in Vancouver. All right, so as I said, I'm going to try and give an absolute whistle-stop tour through jets and cosmic explosions. Quick thanks to a number of collaborators who've assisted me with various graphics and figures. All right, so we see jets right across the universe. We've known about jets for about 100 years. And now, thanks to some of the fantastic current capabilities that we have available, things like the EHT and also SKA precursors such as the ngVLA, we're able to probe these jets from scales of a few hundred RG or even in M87 down to just a few RG, all the way out to scales 10 to the 10 or more times larger. And so you see here our nearest radio galaxy, Centaurus A. So we've got centimeter VLBI image on the left, and we've got an EHT image in the center, and we have an ngVLA image of the enormous radio lobes blown by the jets on the right-hand side. And so these observations are absolutely fantastic for probing the structure of the jets and their impact on their surroundings. As we heard from Anton this morning, the EHT is also probing the actual photon ring around the black hole, and then the ngVLA is able to connect that into the accretion flow. So as he showed, here's an image from Liu et al., where we see the accretion flow in that ring-like structure at the bottom, and how that's connecting into the jets, and how the jets are then being collimated, potentially suggesting the presence of some kind of an accretion wind that helps to collimate the jets, that leads to this outflow that we're seeing in Craig Walker's famous M87 movie from a few years back. So these jets that we're observing in M87 and in Centaurus A, these are all relatively low Eddington rate systems. They're not accreting at particularly high fractions of the maximum theoretical luminosity that they are allowed to have. In order to do that, we need to go somewhat closer to home and look at some of the most energetic events that we see out there in our universe. So these sorts of events, from gamma ray bursts through to tidal disruption events, neutron star mergers, and X-ray binaries, these allow us to ask a number of different questions. We can never hope to probe the jets on similar physical scales in terms of gravitational radii as we can in these relatively nearby AGN, but we can look at the most ultra-relativistic jets that we are aware of, and we can look at some of the most extreme and energetic processes in the universe. This allows us to ask a number of fundamental questions about astrophysics, looking at conditions that we can never hope to reproduce here on Earth in terms of extremes of energy, extremes of magnetic field strength, extremes of gravity as well. So we can ask questions about how do black holes form. They form in supernova explosions, some of which are maybe associated with gamma ray bursts. We can ask, what's the black hole population? So what's the mass distribution of the black holes? How do we produce them? What fraction are produced with what masses? Where do they come from? What are their progenitors? We can look at how do black holes grow via accretion and mergers over cosmic time, and what should we be left with at the present day? And then we can look at their feedback effect on their environment. So, quick disclaimer before I get into the details. I'm not an expert on every topic that I'm presenting here. A number of experts will be speaking after me. There are some fantastic talks to come, and also a number of excellent posters out there, and I recommend that you go and have a look at those. Apologies to anybody I've missed in this list, and once again to flag that there will be a talk on fast transients and pulsars from Sarah on Friday. Okay, so the first topic, stellar deaths. So what can we learn about the deaths of massive stars that are going to give rise to these compact objects, these black holes, maybe neutron stars, that will form from the collapse, the core collapse, when the clock runs down on a massive star's life. It runs out of nuclear fuel, can no longer support itself, and it will collapse. Now, depending on the state of the progenitor star, its rotation rate, its mass loss over its lifetime, any potential binary interactions, we can get a variety of possible different outcomes, ranging from normal supernovae through to gamma ray bursts, and then some of these recently discovered fast blue optical transients that appear to be sort of somewhere in that middle ground. The outflows are not highly relativistic as they are in the gamma ray bursts, but nonetheless there are radio outflows that we can probe with our radio facilities. So these events, they span quite a wide range of energies and Lorentz factors, ranging all the way from the supernovae that you see in gray in the left-hand plot that are non-relativistic, outflow velocities of tens of thousands of kilometers per second perhaps, through to the mildly relativistic events such as these fast blue optical transients shown in the red stars there, out all the way to the ultra-relativistic gamma ray bursts where we can have Lorentz factors of a few tens or even 100 and more. How do we figure out these physical parameters? Well, those come from the broadband spectra of the events that we monitor with our telescopes, particularly in the radio band. So you can see here some work from Sari et al. On the right-hand side, showing that these synchrotron spectra, they're characterized by a number of characteristic break frequencies. And by locating those frequencies and watching how they evolve over time, and then modeling them, we can predict the physical parameters of the events themselves, so energies, Lorentz factors, etc., but also of the environment that they're in. So what's the environmental density that affects how the shock that's driven by these blast waves will progress through the surrounding medium, and allows us to therefore probe what that medium looks like. Okay, so because we can probe what the medium looks like, we can start to track back in time and reconstruct the mass loss history of that massive progenitor star from which, that gave rise to this cosmic explosion. So the radio waves, they probe the fastest ejector from the explosions in a supernova. And because they're moving quickly, they can sweep out a large volume in space. So across the top, I can make the pointer work. Across the top here, we see the time before the explosion that's being probed by the radio observations. So we see here, this is 7 years worth of observations of a particular supernova, I think it's 2004C. And we see the density, the inferred density of the environment from looking at how the spectrum, the radio spectrum evolved over time. And this showed in this particular case a relatively flat density profile that broke after a period of time to give something significantly steeper. So as the shock moves outwards, we're probing longer and longer before the explosion. So this is recreating the last few thousand years worth of the life of that massive star. And so we can look at what are the mass loss histories of these progenitor stars. That tells us something about the relatively poorly characterized mass loss rates in these very massive stars at the ends of their lives. That has an important impact on the future compact object that will be formed in the explosion. And so understanding that mass loss is critical to figuring out for instance, the black hole mass distribution that we might expect to come from those massive stars at the end of the day. There are substantial uncertainties in some of the modeling. So in terms of the fraction of the energy that goes into the electrons in the magnetic field, there's an assumed wind velocity in this case. Pinning down those parameters will be able to get much more accurate values for these. And then they can be compared to other measurements of the wind mass loss rates and theoretical expectations. All right, so moving from supernovae up to GRBs, a certain subclass of supernovae can be associated with GRBs. These are type 1bc supernovae. The GRBs themselves, these are fairly rare events. Not a fairly small fraction of supernovae are associated with GRBs. But as I said before, they have the most highly relativistic outflows. We will hear a fair bit more about GRBs later on in the session, I believe, so I'm not going to dwell on them for too long. But in short, we have this relativistic blast wave that moves out into the surrounding medium. We get a forward shock that moves out into the medium itself, from which we can understand or figure out the circumburst density, the total energy of the burst, and also how collimated that jet is. And then a reverse shock moves back through the jet itself, and that carries some particularly important information, the jet Lorentz factor, and it can also be used to figure out jet magnetization and therefore potentially its composition. I'd also like to note that these GRBs Some of them are detected right out to the edge of the visible universe. So the most distant GRBs, certainly one at redshift of about 9.4, and there's been a claim of one at about a redshift of 11. How far out in time we can go, how far out we can probe with a new generation of radio facilities, that will allow us to start looking at some of the events coming from these very first black holes to have formed in the universe. Okay, so just a quick illustration of how some of this modeling is done. So here we've got a sequence of images showing the progression from about 1 day after the burst to about half a year after the burst of how that spectrum evolves. You can see it's made up of two main components. You have the forward shock shown as the dashed lines, and then the reverse shock shown as the dotted lines. So you can see that over the first few days, the reverse shock dominates the emission at these gigahertz frequencies, and then it rapidly fades below detectability, and everything becomes dominated by the forward shock. From the reverse shock, we can actually figure out whether or not the jets are pointing flux dominated or whether they're baryonically dominated, because something that's pointing flux dominated shouldn't have a strong reverse shock. We won't see it. And so with rapid response monitoring, high sensitivity across multiple frequencies, we can start to reconstruct the actual properties of these explosions and start to answer the questions about what is the nature of the jets coming from these highly energetic processes, where we get Lorentz factors up to 100 and more. Okay, before I finish talking about stellar explosions, I did just want to touch on type 1a supernovae. They're not core collapse of massive stars. These are when a white dwarf exceeds its Chandrasekhar mass and collapses. So this can either be as a single degenerate system, so it's accreting from a less evolved star, or a double degenerate where two sub-Chandrasekhar white dwarfs merge to give a single super Chandrasekhar mass system. Using radio waves, we can try to look at, again, the blast wave from the supernova as it propagates out into the surrounding medium. If we have a double degenerate system, that medium shouldn't be particularly dense, whereas if we've got a non-degenerate source from which the white dwarf is accreting, we can have some material in the surroundings, and then the shock wave moving through that can give rise to radio emission. To date, no radio emission has been detected from this class of events, which rules out a whole region of parameter space shown in gray here. And there we can see that a lot of these models, for instance, a red giant donor, are completely ruled out by the existing observations of some very nearby events. However, we get only about one supernova, type 1a, expected every 15 years within about 8 megaparsecs. As we go further out, we need higher sensitivity. So if we're able to push out to 25 megaparsecs, for instance, we can increase the rates, and we can really start to rule out some of this parameter space, and then either get a radio detection of one of these type 1as, or completely rule out the single degenerate model for these systems. All right, moving on. Now I'm going to move on to the subject of black hole growth via both accretion and merger events. So we'll talk about tidal disruption events, we'll talk about gravitational wave mergers, and we'll talk about X-ray binary systems. So tidal disruption events. Around most supermassive black holes, we can probe the jet structure in exquisite detail, as I showed you earlier, but we can't see how the jets are actually launched, right? The only time that we can see the launching, the creation of a newly born jet, is when we dump a large supply of gas very close to the event horizon of the black hole. And this happens in a tidal disruption event, where we have an unlucky star that comes too close to the event horizon, gets pulled apart by the strong tidal forces, and some fraction of that mass will be accreted with the rest expelled to infinity. So some of these events can be extremely bright. We can see them out to large distances, redshifts of 1. But these are very rare. Maybe only a few % of tidal disruption events have these ultra-relativistic jets. Again, Lorentz factors can be a few tens or even 100 and more. Now, the advantage of these is that we can use them to, again, probe the density profile of the surrounding medium. We can fit these broadband synchrotron spectra to look at what is the density of that medium that it's propagating into. So this is telling us about the density profile at parsec scales around a supermassive black hole, which is very hard to probe by other means. And that can allow us to try and reconstruct the accretion history of the black hole itself. So here you see the most recent, so only the fourth of these jetted TDEs that's been detected to date. This was AT 2022 CMC that went off just over a year ago. And here is a year's worth of monitoring as it evolves from the dark colors through to the lighter colors. We can see the synchrotron peak frequency moving to lower frequencies over time, and fading. And from this, we're able to reconstruct some of the key physical parameters of the event. TDEs have also been associated with high-energy neutrinos, at least a suggestion to that extent has been made. This event, AT 2019 DSG, it showed it was a thermal tidal disruption event, so it didn't have a relativistic jet pointing straight at us, but it did have reasonably bright radio emission for a non-jetted system. However, the inferred Lorentz factor and kinetic energy for the event were not particularly large, which has cast doubt on that association. Now, if we can get more of these events, particularly going deeper into the universe with radio follow-up, getting better precision with the localization from the next generation of neutrino detectors, this could be an interesting connection to try and probe to see if indeed there is a connection there or not. As well as these jetted tidal disruption events that I said were only a few % of the population, we also have a class of systems called the thermal tidal disruption events, where there is no jet that's beamed right at us. And in fact, we can rule out a relativistic jet for any possible viewing geometry. In this case, we're still trying to figure out where does the radio emission come from. Is it from accretion-driven winds moving out into the surrounding medium? Is it due to the tidal debris streams crossing over with each other, interacting, creating shocks, which drive these outflows? Or is it the shocks created by the unbound tidal debris that's just moving away to infinity? Trying to disentangle that, again, we have to figure out the physical parameters of these events. Once again, this comes down to this broadband spectral modeling. You see an example over here from Adele Goodwin. And here are the light curves of a number of these events that have been seen. You see a wide range of behavior, different rise times, even some very, very late time flaring a few years after the disruption itself. So how do we distinguish between these scenarios? Well, we need to get the physical parameters out of the modeling, and we need to try and get a more complete sample. We've actually only got a relatively small number of events to date. It's about 16 with published radio detections. And you can see here that there's only one detection above a redshift of 0.1. We don't have a complete sample. A lot of these upper limits wouldn't rule out some of the closer detections that we have to date. And so we don't have enough to be able to correlate the presence of radio emission with other physical parameters of the event that we derive from optical monitoring and so on. Pushing down the sensitivity using these new facilities, ngVLA or even SKA, that would allow us to get a uniform sample here in the range of luminosities that we see these sorts of events occurring, and to start figuring out what it is that drives the radio emission. When do we expect radio emission from these events, and what is causing it, and get a better understanding of what's going on in these very high energy processes. Lastly, we can actually move away from the broadband modeling, and we can say astrometrically, can we detect outflowing jets or winds or whatever? We can compare the speeds that we infer from the modeling to something that's directly measured. At a redshift of 1, a jetted TDE would have a proper motion that's eminently detectable with, for instance, the long baseline component of the ngVLA. And similarly, at a much lower redshift, we could measure a mildly relativistic outflow from a thermal tidal disruption event. This has been tried in the past, so a couple of examples here. There's been no detected motion in either case, possibly because of the late time monitoring in this event, when the outflow may already have decelerated, and due to the relatively short time baseline of this one over here. But this is certainly something that, a question that we can address. We can actually start to look at the motion of the outflows that we're getting. All right, there we go. Moving on from tidal disruption events to gravitational wave mergers. So these are some of the most exciting events in transient astrophysics at the moment, allowing us to explore kilonovae, arc process nucleosynthesis, energetic jets, and even making a measurement of the Hubble constant. All right, so talking about astrometric shifts, superluminal motion, whoops, let's go back. Superluminal motion was detected in gravitational wave source 170817, this binary neutron star merger, detected in 2017 at a distance of about 40 megaparsecs. This astrometric shift was crucial in demonstrating that the event did launch a highly collimated relativistic outflow, which was used in conjunction with modeling of the radio light curves, the rise and decay times, to validate that we think there was a structured jet in the event, so a relatively rapid jet that drove this cocoon that you see in red here into the kilonova. We're viewing it a little bit off-axis, and we could constrain the opening angle. So from these detailed observations of both the light curves and the astrometry, the VLBI observations, a full physical picture of the event was able to be pieced together. The system has remained detectable for about 3 years. Over here, some of the latest constraints on it. Now, in theory, we might expect to start seeing some radio emission from the kilonova afterglow as that propagates out into the surroundings. That hasn't been seen yet, which gives us some constraints on the velocity profile of the kilonova ejecta, which will depend on the neutron star equation of state. So again, some very interesting physics to be done there, but we need high sensitivity to be able to do this. Lastly, because we can get the luminosity distance directly from the gravitational waveform, the redshift from the electromagnetic data, we can make a measurement of the Hubble constant from these sorts of measurements. And the VLBI motions there were particularly important in breaking the degeneracy between the distance and the inclination angle of the event in the gravitational wave data and getting a much better precision on the Hubble constant measured in this way. With 50 to 100 of these sorts of systems, we could get a precision down to about 2%, and that would give a measurement that was independent of the cosmic distance ladder and also the cosmological model on which the Planck and the supernova and Cepheid measurements are dependent. And we have this tension between the two of those that could help to try and break with more of these merger data. However, 170817 was relatively nearby, only 40 megaparsecs. The LIGO horizon in the current 04 run will go out to about 190 megaparsecs, and future generations 05 and into things like LIGO Voyager, Cosmic Explorer, will move out to much greater distances, at which we won't be able to get light curves at all. We won't be able to get radio detection. So we need to push down the sensitivity if we're to realize the potential of these events. Okay, here's some nice work by Alessandra Corsi showing that the ngVLA could not only pick up the various different components of the relativistic jets launched by these merger events from the reverse shock through to the forward shock viewed off-axis potentially and the kilonova ejecta, being seen at different time scales and with different flux densities, and here's the ngVLA 1 hour sensitivity. Note the very large range of flux densities on the x-axis, so the y-axis here, it's many, many orders of magnitude. But here, the visibility plot shows that it could, in principle, distinguish between different the geometry of the ejector in those events. So there's a lot of very interesting work to be done, and I think some talks later in the session will touch on this a bit more. Okay, moving on to X-ray binaries. So these are accreting black holes in our own galaxy. They're known to launch jets. We can study those in the radio. Now, we can look at these jets from the launch point all the way through to their termination. So this is a movie made with a VLBA of the binary system V404 Cygni, where we have jet components propagating outwards. And observations have shown we can track these out from these milli-arcsecond scales all the way through to arcsecond scales. Here's a Meerkat movie from the Thundercat project showing jets moving out at arcsecond scales. This allows us to get the total energy from the events, and we can try and connect the events to the accretion flow itself. However, the trouble with the sensitivity and the UV coverage of current arrays is that moving sources that are variable can't be imaged directly. And we need to develop new algorithms in order to image them, otherwise we'll get significant artifacts in our images. Trying to connect those jets to the accretion flow requires accurate launch times, and so we really need these VLBI observations to constrain those. We've got those down to about 30 minutes here, which we can start to connect to X-ray observations to figure out what events in the accretion flow cause the launching of jets. We can use those jets as probes. We can get natal kicks from proper motions, distances from parallaxes, and even the inclination angle of the orbits if we can trace the orbits on the plane of the sky. That helps us break the degeneracy between the mass and the inclination angle, and therefore get an accurate black hole mass distribution, which we can start to compare with other populations of black holes seen by LIGO and also detected in Gaia data to explore things like the mass gap that exists or is thought to exist in these events. We're going to look at the mass distribution of stellar mass black holes. I'm going to finish up with just a couple of slides looking at what we can do by pushing to very low sensitivities in the galaxy. So here we have 480 hours of ACCA observations reaching sub-microjansky noise levels that have detected in the globular cluster 47 Tucani a central radio source that could be either an undetected pulsar or potentially even an intermediate mass black hole, which is quite exciting. We can look for some of these very quiescent low luminosity black holes through astrometric motions in deep radio surveys. And if these systems show a motion with time, potentially even a parallax, we know they're galactic, they could be new quiescent black holes, again, increasing the population. Finally, just to say, the discovery space in the galactic plane is quite large, and I'm just going to highlight as a taster these long period pulsating sources discovered in MWA data by Natasha Hurley-Walker and collaborators. We can find those through the galactic plane, but scattering obviously makes life difficult. But these are very interesting objects, an 18-minute period here. So potentially a new class of source. We're not quite sure what it is, but there's a lot of discovery space that's out there. Okay, so I'll wrap up there. Here are some of the advantages that we will get from these very high sensitivity new facilities. I'm really looking forward to what they can tell us about jets and cosmic explosions, and I'm happy to take questions. Thank you.
Thank you very much. Now, questions? I'm sure you have some questions for James. I forgot to mention that his talk was an invited talk. There is questions in back.
So, nice stuff. I can't wait to see the next generation of telescopes. So any number of questions. The one I'll ask is about the supernovae and such, where you're looking at the mass loss history versus time. How much of the mass loss that you know must have taken place have you actually been able to trace in this fashion? In other words, what fraction of the mass that you think must have been lost to get from whatever 15 solar masses to whatever you think you wind up with have you traced out by looking at these light curves with time? And how far down would you have to push things to make that an interesting fraction?
So, quick disclaimer, this is not my direct area of expertise, but I will say a lot of the mass loss that is actually, this occurs over the lifetime, particularly the late stage lifetime of these very massive stars. I think a few thousand years is not sufficient to really probe all of the phases that you'd want to look at there. And so I think we're limited by the time horizon that we can get. Obviously, pushing to higher sensitivities would allow one to track these things for longer. Whether that can ever get to enough of the history that you're interested in is an interesting point, but I would have to defer to other experts on that one.
Yeah, you mentioned at one point that
please wait for the microphone.
So you mentioned at one point that you could look at the reverse shocks to tell whether you had a baryon loaded or pointing flux jet. Is there a reason why you didn't consider a leptonic jet?
I think a pointing flux jet should generate these electron-positron pairs, right? And then you've got this leptonic jet that's tracking outwards, right?
Okay, but you could have something where most of the energy is being carried in the magnetic fields rather than in the pairs, right? Or is that not possible?
So the point is that if there's too much energy in the magnetic field, then you're going to get a relatively weak reverse shock. Right. And so that's where the distinction comes in, to my understanding. But I think later speakers may well cover that in more detail.
Yeah. Thank you.
Over there.
If I understood you, first of all, very nice talk. If I understood you correctly, you made a comment about the problem with imaging fast-moving objects. Mm-hmm. Is that just the fact that we haven't had to deal with it, so we haven't dealt with it, or is there actually a fundamental issue that we need to understand?
So it's something that probably should have been dealt with over the last 2 decades since the discovery of relativistic jets within our own galaxy, the microquasars, and it's hindered that. And different approaches have been taken, imaging small fractions of data and so on. Snapshot imaging has its limitations. It's not using all the information that's contained in the data. And particularly when you don't have either a sensitive array or a lot of stations, so your UV coverage is good enough for snapshot imaging, that's not an ideal approach. And so developing new algorithms to be able to actually model what's going on, whether it's in visibility space, whether it's using some of the new algorithms that are being adopted by the EHT, should allow us to get an awful lot more out of the data and actually pick up things that we would not have seen otherwise.
Okay, one last question here.
So I was interested in the fact that you pointed out that there were no detections of type 1a supernovae in the radar. I presume that this is because they tend to explode in very low density environments?
Yeah, so this is the thing. If you have say a red giant donor, the environmental density is significantly higher than if you've just got two white dwarfs that merge. And so the presence or absence of radio emission can act as a discriminant between those two potential formation scenarios for the 1A, whether you've got merging white dwarfs or a single white dwarf that's accreting. And so depending on what the companion is, you'll have different densities in the environment. And those were some of the different blocks that I was showing on that plot.
Okay, so this is a very close-in environment to the exploding star,
Yes.
not the farther out environment. No. May have different densities.
No, I mean, it's a supernova. There's no jets. So, I mean, any blast wave velocity will be, a few thousand kilometers a second or something.
Thank you.
Okay, I think it's time to move on to the next talk. Thank you so much.